So chapter 18 mostly, without me saying it explicitly, dealt with molecular spectroscopy, where we were talking about transitions in a molecule. So we talked about electronic transitions between electronic states in UV and visible regions of the EM spectrum, but also vibrational and rotational transitions that were required less energy and sort of subdivided those electronic transitions and vibrational transitions respectively. We talked about fluorescence and how what's actually happening is both an electronic and a vibrational transition simultaneously, and then a sort of vibrational relaxation to a photon emission, and that happens at a longer wavelength. What I want to talk just briefly about here, which you didn't get a chance to do probably in the Flex version of this class, but is this notion of atomic spectroscopy, which is a really common version, but instead of dealing with a molecule, we're dealing with the electronic excitation of an atom. And it ends up being really similar in the construction and the geometry of the spectrometer, but the types of signal that we get are distinctly different, simply because we're dealing with atoms instead of molecules. So I'll first start about the types of atomic spectroscopy that can be done, namely the types of transitions. Then I'll think about how those are distinctly different from molecules. So we have a few different that are highlighted here. There's of course more than this, but these are sort of the big common three. We have atomic absorption, which is in the center here, this type of transition where you have the ground state electron. And when we're talking about atoms, we're literally talking about something like lead and measuring the absorption of light on a lead atom, typically in the gas phase. So we're talking like lead gas. So what that means is instead of having electrons arranged in a delocalized set of orbitals that we call molecular orbitals, of course there's no molecular orbitals on this, there's just the atomic orbitals. So 1s2, 2s2, etc. up through its electron configuration. So we could figure out what the electron configuration is for lead. We write up all the possible atomic orbital states. So it's actually a lot simpler in that way, because there are only electronic transitions, and the electronic transitions are pretty well defined. And when I say there are only electronic transitions, what I mean is this thing can't vibrate, because for something to vibrate, you require at least two components and a bond between them. So there are no vibrational modes and there are no rotational modes, because this thing doesn't have an axis to asymmetrically rotate about. So the transitions are much simpler for atoms, which makes it a really simple technique to use. So for atomic absorption, it's exactly like molecular absorption, except simpler, because there's really limited number of transitions that can occur. So you've got an electron down here in the ground state. If a particular wavelength is sent in to the atom in the gas state, we can promote that up to any one of the higher order orbitals that are unoccupied at that time. So you see two different absorptions here. You can also have atomic emission transitions, which is sort of the corollary to molecular fluorescence, where you have the absorption of a particular photon or an excitation, which may be photon induced or not. It could just be thermal, where we just heat this thing up so much that all of the electrons are just sitting in higher energy states, and then they just spontaneously move back down to the ground state as maybe they move out of the thermal equilibrium or for whatever reason, and they emit a photon. And so that would be an emission type. And then we have these sort of atomic fluorescence transitions, which just involve one of these non-radiative transitions, which before we talked about with squiggly lines, where you have an absorption step and then you have a non-radiative transition to emit a photon of light at a longer wavelength. So what changes about the molecular geometry? Well, only really one thing. So the geometry is really the same, or at least it draws significant parallels to a normal spectrophotometer, molecular spectroscopy geometry that we talked about before, where we have some sort of light source, some sort of sample introduction method, some sort of wavelength selector, and some sort of detector in a geometry that looks comparable to this. There's a couple things that change here though. For the absorption, or really in any of these scenarios, we're talking about absorption of light of a metal, and in that case we need to get that metal by itself. So typically these samples are aqueous samples where we want to measure, or they don't have to be aqueous, but when we talk about a metal, we're not talking about like a slab of lead. We're talking about lead dissolved in something. So lead in water, or lead in oil, or lead in some sort of substance. And in order to get that lead atom into its atomic form, specifically into a gas form, we need to sublime it, and so we have to put in quite a bit of energy to get it into that gas state. So it's not interacting with other lead atoms, it's by itself in the gas, which gives us access to those really well-defined and discrete atomic orbital energy levels. And so we put heat into this thing, and so instead of having a normal cuvette, we replace that with a flame. And so if you were to see this in person, and I'll show you a short video, most atomic absorption spectrometers just have a little furnace in them, and you literally just pump a little bit of your sample into the flame, and what happens is it completely evaporates all the water almost instantaneously, and so what you have left are all the solids, or in this case ions, that sort of come together rapidly, and those ions can then break apart, and you're left with the ion or the metal, depending on what state it's in, and that then sublimes to the gaseous state, or we call that atomization. That all happens fairly rapidly in the flame, in the core of the flame, and so what you have then is a cuvette that is essentially a flame, where Beer's law, absorbance equals epsilon concentration path length. This path length, instead of being the cuvette, is now the width of the flame in the sample introduction here. So it's actually really comparable. We're still doing spectroscopy in a way that's still linear, with concentration absorbance, as the Beer-Lambert law would suggest. We're just changing the way that we're introducing the sample because we need to get it into this atomized state. So that's the first thing that changes. The second thing that changes depends on the type, the specific type of atomic excitation that you want to do. Whether you want to do atomic absorption, which is the most common, emission, which is the second most common, and fluorescence, which is the third most common. And that has to do with the light source. So in at least for really all three of these, we're not using a broadband source like an incandescent bulb that I have shown here. So we're not using that specific light source, but for, say, atomic absorption type measurements, we replace that light source with what's called a hollow cathode lamp. And what a hollow cathode lamp is it's essentially it's similar to like a discharge lamp that that you would have seen in like a Chem 107 when we talk about line spectra. So like a neon lamp, that type of thing where you have a single element inside of this thing. You've got a couple electrodes inside of this thing, and the electrodes, at least one of those electrodes, is made up of the element that you seek to measure. So in this case, you actually get a hollow cathode lamp that has a cathode made of lead, and then you bias these, you apply a large voltage between these. This is evacuated, so there's a vacuum inside of here, and what you do is you pull electrons off of the positive electrode, and then they rapidly accelerate towards the negative electrode. Those electrons smash into that lead, or whatever the element is, cathode, and they excite the lead to a lead star, to some excited energy level, atomic energy level. As that goes back down to lead 0, it emits a photon of light, and that photon of light has exactly the same frequency as the lead absorption transition. So you're essentially sending in monochromatic light. You may be having multiple transitions in lead, so it's not truly monochromatic, but the only light that's being emitted from the lamp is coming from lead excitation. And so you're essentially tailoring your absorption measurement to that specific element, which is nice because then you have inherent selectivity where the only thing that should be, and this isn't always true, but ideally the only thing that should be absorbing then is that element if it's inside of the flame. And so if you have lead then in the flame, it will absorb that very specific frequency of light and then go through its own excitation. And when it absorbs, that means less light is hitting the detector. And so it's the same thing where we measure a blank sample and a regular sample, and we take the ratio of those to deduce our absorbance. We also have a monochromator because of different stray light. There's a variety of different other things that could be happening here, or these atoms could be emitting light on their own because they're thermally being excited, and so we can then select for the specific light that we want to get through, so that it doesn't completely nullify the existence of the monochromator. We still have that in the system. So, you know, the painstaking part of atomic spectroscopy, at least in this format, is that it's not very good if you want to measure lots of different elements in the system. If you say, hey, I want to characterize all the heavy metals that are in my drinking water sample, that might be 15, 20 different things. That means you got to swap out your hollow cathode lamp every single time you want to change elements. There are lamps out there that have multiple metals as the cathode, so you can do a few different emissions and absorptions simultaneously, but it's still a pretty energy and resource and time intensive process, though the overall instrument is quite cheap because, you know, it seems like you're doing an exotic spectroscopy here, but really you've just got a flame and a lamp and a monochromator and a detector. And so these things are actually quite easy to construct, to build, and to maintain. They're pretty robust. That's absorption. So if you want to do atomic emission, that's a little bit different, because in that case you actually don't need a lamp at all. But what you need to do is dial up the temperature of your flame such that a large proportion of the atoms you're interested in, if those things are lead, they're existing in excited electronic states inside the flame. So notice that in atomic absorption, the flame is sort of designed, at least the temperature, to atomize everything, but you don't want to also add enough energy that everything is in an excited state, because that's why you're sending in photons from the hollow cathode lamp. Emission is slightly different in that you want those to already be electronically excited, but instead of adding a photon to do that, you're just adding heat. So you have this flame at a higher temperature. And what's nice about that is then there's no lamp at all required. It becomes a really simple instrument. You just have a flame, you bleed in some of your sample into that, it atomizes and excites, and then all of the atoms inside of that system are going to emit based on whatever their thermal excitation is. So it requires a little bit more dialing in, but it becomes pretty sensitive in that case, because similar to fluorescence, you don't have this background light that is hitting the detector. The only thing that's hitting the detector is emission from the atoms inside the flame. And so emission can be a pretty nice technique. It's also really, really simple, because you just have a flame, a monochromator, and detector, and that's it. You actually have no light source at all. The light source is literally the excited atom in this case. Of course, you may be exciting multiple atoms at that same time, depending on what's in your sample, which necessitates the use of a monochromator again in this case. The last type of atomic spectroscopy is the fluorescence type, which is really similar to emission, except that we're not thermally exciting those atoms to higher atomic orbital states. We're doing that with a laser. And a laser is essentially a light source that has a fixed wavelength. So it's got one wavelength, and it emits a flux of photons that are coherent, collimated typically, and pretty intense. So you have a high density of photons. And so what that does is it just pumps a bunch of ground state electrons into a higher energy state, and you can dial that in specifically for the atom that you're interested in, and then it will fluoresce. The fluorescence is similar in that the geometry required for this is probably one where you want this detector to be off-axis, which is what you see here, where you have your laser that's coming in, and then you have your detector. They're not at 90 degrees, but they're not. So if you follow the path of the laser, it's not going to hit the detector. And that's the benefit of fluorescence, again, is that it becomes a very sensitive technique without the added background. So just a quick clarification too on what the nature of that absorbance spectrum might look like if you were to collect a full spectrum, which you often don't. But it's important to recognize the difference between a molecular spectrum and an atomic spectrum, or a molecular emission or an atomic emission. As we mentioned in the previous videos, if you have a molecule, an absorption spectrum for a molecule, which I'm showing in blue here, it's very broad, the absorption, and the reason for that we mentioned is that subdivided inside of, so maybe, you know, these two absorptions actually are from two different excitation states, from n equals 1 up, or n equals 1 to 2 and 2 to 3 or whatever. But what we also know is that subdivided inside of these electronic transitions are several vibrational states, and then subdivided inside of those vibrational states are rotational states. And so when you're exciting these molecules, you're exciting electrons into a variety of these states, which leads to sort of an underlying spectrum like this, but we don't actually resolve all of that fine structure, vibrational and rotational, simply because these things are in solution. They're colliding with each other and they're transferring energy very rapidly. And so that sort of smooths everything out into this broad and distorted molecular absorbance spectrum. What's important to note, though, is that with an atomic type absorption or emission, we're only bound to the atomic orbitals of the atom. There's nothing else bound to it. So there are no vibrational states, there are no rotational states, and they're in the gas phase, meaning they're not bouncing around in solution, losing energy to each other. So an atomic absorption spectrum is very sharp, almost like a delta function. It doesn't cross over like that, but it would be very, very sharp, simply because that transition is well defined from one state to the next. There's nothing else that gets excited in that state. It goes up and then it comes right back down. And so we call that an atomic spectrum, or what you would have learned in like a Chem 107 class or a 108 class is we'll call these line spectra. And the reason they're called line spectra are because they're very sharp absorptions, often so sharp that they're only occurring at like single nanometer widths. So they almost look like straight lines instead of these broad distributions. And we talked about this when we talked about the structure of an atom. Right, this was how the structures of atoms were deduced early on, were the atomic line spectra. We put these atoms as gases in these discharge lamps, which are really similar to a hollow cathode lamp, like a neon tube or a hydrogen gas tube, a helium tube, right? And they glowed, but they didn't glow white light. They glowed one specific color, and that specific color was whatever the line spectra. Often there are several, because there are several atomic transitions that are being excited in those discharge lamps. But instead of a broad sort of distribution of light like we'd see from an incandescent bulb, we see these discrete bands. And so you might have worn these spectrograph glasses and seen that in the past, but just to highlight the difference here, which makes it nice because it's a little bit easier to differentiate atoms, because you know, one atom may have a band series that looks like this, and then another one may be really close, but still resolvably different, because the width of those peaks, the absorption or emission peaks, are so narrow. Okay, I want to show you a quick animation. This is actually pretty nice walkthrough just of how an atomic absorption spectrometer works. So we have one that looks just like this at CC. So I'm going to play this video. So first thing on the far left is our light source. So we'll see these hollow cathode lamps, and you can see this is on sort of a rotating thing, so you can have several already built in. This is the mechanism. So you've got the copper plate, because we're trying to measure copper, and that excites copper to a higher energy state. That electron then emits a photon as it decays back down to ground state. Those photons, that creates light, but of a monochromatic type of light. Here we're sucking up some of the sample. Those are copper ions in a water sample. Those go into the flame. This is just a graphite furnace. They're coloring that flame because it's copper and there's an excitation. And as one of those photons strikes a copper atom, it gets excited to, again, a higher electronic state in its atomic orbitals. And then it absorbs that light. Right? And so that's one photon that doesn't make it to the detector. And that's really the general principle for how an atomic absorption spectrometer works. There's an iron atom, not enough or exact energy for it to excite that atom because energy is quantized and those atomic orbital energy levels are distinct. Okay.